Okay, this is working for the mechanics part of the AS June 2019 maths paper, questions 1 and 2. I've already done the working for, or most of the working for question 1, just to speed up the process, because I think part C was a tricky bit. Part 1 was the first stage of the journey. You've got 3 stages of the journey. The parachutist jumps out of the helicopter. The parachutist then opens up her parachute, so she slows down. And once she slows down, she's reached a particular speed which she stays at that velocity for until she hits the ground. Working for the first bit is, you know that U is 0, you know acceleration is 10, they tell you that, you know she does that for 3 seconds. So you can work out quite quickly that velocity she reaches at this point is 30. So that's why I've got a 30 there in 3 seconds. The second stage of the journey, she decelerates at 12 meters per second for 2 seconds. So she will lose 24 meters per second. She was 30, she loses 24, she goes down to 6 meters per second. So that's the jumping out of the helicopter and accelerating quite quickly. Opens the parachute, decelerates, and then finds a constant speed all the way down to the ground. So here's my work, and there's the velocity at that point. I've worked out the velocity at this point is 6. So there, part B, there is my graph. Part C is the slightly tricky bit. Part C, we're working out what the total time is. We know what the total distance travelled was, is 550. But we want to work out what this value t is. I shouldn't actually have a line there. Now, on a velocity time graph or a speed time graph, the total distance travelled is the area underneath the graph. So we know that this total area is going to be 550. We can work out the area of this triangle quite easily. Half the base times the height, half the base times the height. There's a trapezium. The long length is 30, the short length is 6, the height is 2. So it's half times 30 plus 6 times 2. And then this rectangle here, well, this height is 6. This length here, well, if that's t and that's 5, and this whole length is t, take away 5. So there's the area of the rectangle. I know these 3 areas, that one plus that one plus that one, this one plus this one plus this one, has to equal 550. So just sorting out the numbers, that's 45, that's 36, that's 6t, take 30, equals 550. Sorting out the algebra, 6t is 499t is 83.16. And part C says find to the nearest whole number the value of t. So t is therefore 83 to the nearest whole number, 83 seconds. Part D, in a refinement of the model, the effect of air resistance is included. So therefore, this is not going to be as steep, she's going to be slower. Presumably she'll find a similar speed down here, but it means that the total area underneath here, in order to be 550, t is going to have to be extended. So for part D, all we're looking for, t would be greater. And part E, another refinement to the model, apart from air resistance, to make the model more realistic. Well, we've got acceleration here as 10, that really ought to be about 9.8. We could have the effect of wind, presumably working in a fairly horizontal fashion, although any wind blowing up or down would slow her down or speed her up further. You could have things like this, unlikely that this acceleration is going to be very uniform, particularly at this point here. The deceleration is not going to be sudden. You'd have a curve here and you'd have a curve here, both of which would change the value of t as we try and get this area to be 550. And that's question 1. Right, question 2 was a Puller's question. Just finding it on the paper. This weight here is 0.6 kilograms. This distance here is 0.4 meters. This weight here is 0.8 kilograms. That distance is 1.5 meters. So we've got a small ball of mass 0.8. This is P and this is Q. It's held at rest on a smooth horizontal table attached to one end of a thin rope. There's my very poor drawing of a thin rope. The other end of the rope is attached to another ball, Q, of mass 0.6 that hangs freely below the pulley. Ball P is released from rest with the rope tight taut, it says, with P at a distance of 1.5 from the pulley and Q at a height of 0.4 above the ground. Ball Q descends, hits the floor and does not rebound. So the balls are modelled as particles, the rope has a light and inextensible string and the pulley as small and smooth. Using this model, show that the acceleration of Q as it falls is 4.2. Okay, so we're holding this, that rope is tight, this rope is tight. The tension in this bit of string and this bit of string are the same because the pulley is smooth. The only thing moving this whole system is gravity pulling on this one. So we're going to write down our F equals ma equations for these two. So first let's do it for this one. The only force acting on this is the tension in the rope. So T equals 0.8 mass times the acceleration, whatever the acceleration is. Let's look at the equation for this one. We now have two forces acting on this. We've got 0.6 times G pulling downwards and T pulling upwards. And that's going to give us an acceleration, a mass times acceleration of 0.6 times A. We have two equations, we have two unknowns, so we can just solve these. I'm going to solve these by substituting this into here. So 0.6G take away 0.8A equals 0.6A. Move that across to there, so I've got 1.4A equals 0.6G, and A is therefore 0.6G divided by 1.4. 0.6 times 9.8 divided by 1.4 is 4.2, and that's exactly what they were looking for, 4.2 meters per second squared. So that's part A. Find the time taken by P to hit the pulley from the instant when P is released. So let's think about the motion of P. For 0.4 meters, this is accelerating downwards at 4.2 meters per second. The minute it hits the ground here, there's no longer a tension in this rope. And because this is smooth, then this will then move at a steady velocity until it hits the pulley. And that distance will be 1.1 meters. Total distance here is 1.5. This is 0.4, so this will travel for 0.4 meters while accelerating and then at a constant velocity. So let's break it up into those two parts. 0.8, this particle here is accelerating from rest, so U equals 0. We want to work out what V is. We know that A is 4.2 and we know that S is 0.4. So that's the first part of the journey. Let's work out V. So V squared equals U squared plus 2AS. V squared equals 0 squared plus 2 times 4.2 times 0.4. So V squared is 8.4 times 0.4. Ought to be able to do that in my head. 3.36. So v squared is 3.36, so v is the square root of 3.36, which is 1.833. So the velocity at this point, when this hits the ground of p, is 1.833 meters per second. Second part of the journey, we now have u, so the initial velocity if you like, although it's running under constant velocity, is 1.833, and the distance is travelling is 1.1. There's no acceleration, and so we want to work out the time taken. So speed is distance over time, therefore time is distance over speed, so the time taken is going to be 1.1 divided by 1.833, which is 0.6 seconds. Right, so the second bit of the journey took 0.6 seconds. We now need to go back and find out how long the first bit of the journey took. So I've got U, I've got A, I've got S, I've got V. I mean, there's any number of ones I could use. V equals U plus A T. So I've got 1.833 equals 0 plus 4.2 T. So T is 1.833 divided by 4.2. 0.436, so 0.436. So the first part of the journey took 0.436, the second part 0.6. So T, the total time, is 1.036 seconds. Have they asked for? No, that's it. State one limitation of the model. There's all sorts of limitations. We've assumed that the string is inextensible. We've assumed that there's no friction here. We've assumed that the pulley is small. We've assumed that these are particles and not actual balls, all sorts of things. So there'll be wind resistance, there'll be friction within the pulley. All these things limit how this works. Now this part B, I've done it a particular way. There are several other ways at arriving at the same answer, just using your Subat equations.